So therefore, to introduce the topic and just explain to you what is solvent co-intercalation and why should we actually care about it, I would like to start with basically presenting you the situation that we find in most lithium or post-lithium ion batteries. And that is, we have solvated ions in the electrolyte, but at the liquid-solid interface, we have the desolvation step. So the ion needs to get rid of its solvation shell before it intercalates into the host electrode. This causes typically a large charge transfer resistance that can be particularly significant when we are in multivalent systems or in low temperatures. It can also slow down the ion diffusion kinetics because of strong ion-host interactions, Coulombic interactions, and it also limits the feasible combinations of ions and host materials. And one strategy to address all of these issues actually is solvent co-intercalation. So what do we do here is we enable solvated ions from the electrolyte to directly intercalate into the host material together with parts or the entire solvation shell. What this does is it drastically reduces charge transfer resistance and can also increase transport kinetics of the ions in the host. So solvent co-intercalation is actually a phenomenon that is not entirely new. It has been described in literature most famously for solvated sodium ions that can intercalate into graphite, which was discovered by the Adelhelm group in 2014. So they have shown if we use these Klein solvents in the electrolyte, solvated sodium ions can actually reversibly intercalate into graphite. But not only on the negative electrode side, also on the positive electrode side, this is possible. So for example, in titanium disulfide, also solvated sodium with a diclime electrolyte can intercalate and shows different electrochemical properties than the desolvated sodium intercalation. And for multivalent cell chemistries, there was, for example, a work that has shown that solvated magnesium can reversibly intercalate into manganese oxide electrodes, whereas desolvated magnesium was not able to. So we see this is a very promising strategy, particularly for post-lithium systems. But all of this, what we can find in literature, is focused on employing specialized electrolyte formulations. So the electrolyte here is key to enable solvent co-intercalation. The question that I ask myself and that my group is really interested in is, can we actually achieve solvent co-intercalation not by electrolyte design, but by electrode material design? And the core hypothesis that drives our research is that we believe that the properties of this nanoconfining interlayer space between the layers of the electrode material actually drives and can dictate whether we have solvent co-intercalation or desolvated ion intercalation. And this is basically our vision to control the degree of ion solvation by designing this nanoconfining space here. And then, of course, the question also arises, well, what are the electrochemical properties of these co-intercalation reactions? Because we have seen from literature that they also quite differ from desolvated ion intercalation. Well, how can we study such effects? We need suitable model systems. And what is one of the most successful materials so far in my group is the vanadium pentoxide system that also my PhD student Jamila has presented on her poster. And here we regulate the interlayer spacing of the V2O5 by following a hybridization approach. So we include alkyl diammonium pillars of various lengths into the interlayer space here. And the materials that we receive, they vary in the interlayer spacing. So we can vary it very easily between 1 and almost 2 nanometers. And therefore we are able to study what is the influence of interlayer spacing on the ion intercalation properties. And we start with lithium, but we will move on to post-lithium, so no worries. But in lithium, we can see already here in red and green the comparison between small and large interlayer spacing. We have differences in the cyclic voltammogram signature. For larger interlayer spacings, the peak gets much broader. And if we now employ operando XRD to find out what the underlying mechanism here is, we see, so this signal here follows the interlayer spacing. In the small interlayer spacing, we have very small changes only of the d spacing upon intercalation, deintercalation of lithium. So this is the typical solid solution mechanism. However, in a material where we start with a larger d spacing, we get suddenly an even further increase in the d spacing, which, well, is kind of counterintuitive, because if you have more space available, why would it expand further? But our explanation is this is not desolvated lithium intercalation, but partially or fully solvated lithium intercalation that then causes this further expansion of the d spacing. We have submitted this, but the referees were still a bit skeptical whether this is actually a solvent co-intercalation, so they asked us for additional experiments. And one method that is really suitable to check whether desolvated ions or solvated ions are intercalating is EQCM, so electrochemical quartz crystal microbalance. So here we are tracking, actually frequency changes at certain potentials that we then can calculate mass changes from via the Sauerbrei equation. And we can do this here. This is the electrochemical signal of our material with the medium interlayer spacing that we coated on a quartz sensor for the EQCM. And we can track the mass changes during intercalation and deintercalation. The same we can do now for our material with the largest d spacing, where we expect the solvent co-intercalation. And if we now actually integrate these curves and plot the charge versus the mass change, we can, from the slope of these curves, calculate the molecular weight of the intercalating species per electron transfer. And we can see that there's roughly a factor of 8 that the mass per electron transfer is larger in the material that has the most expansion. So this is for us a clear evidence that we actually have the solvent co-intercalation mechanism in this highly expanded V2O5 host. Yeah, and these were really exciting results for us because, well, to the best of our knowledge, this was the first time it was actually shown that electrode design can cause the solvent co-intercalation effect. Okay, so now we would like to also use this phenomenon in calcium intercalation chemistry. And since the start of the year, this is what we have been working on. And we started with an investigation versus activated carbon, oversized activated carbon electrodes. And we see here in blue and green, again, the materials with medium and large d-spacing expansion versus a reference material of calcium vanadium pentoxide. And at low rates, we already see differences here in the peak positions and the general shape of the CVs. And most interestingly, if we now go to very fast cycling rates, so 10 millivolt per second, we can clearly see that the material in green here, the C12 with the largest interlayer expansion, actually maintains quite an impressive capacity. So the kinetics of this system, also for calcium intercalation, seems to be very promising. So now in the future, we need to actually understand the underlying mechanisms here and also expand to calcium metal full cells. So now I talked about the geometric aspects of the nano-confining space, so simply expansion, interlayer spacing. But can we also tune the chemical environment in nano-confinement? And this was a question that my postdoc Hao Cheng has been asking and investigating. Here, again, the vanadium pentoxide system, but in an aqueous zinc electrolyte. So we are interested in zinc intercalation now. And he was tuning the chemistry of the nano-confining space from hydrophilic to hydrophobic interlayer environment. And now we check, actually, is this material design principle valid? And what we find is, in fact, the water sorption capacity for the most hydrophilic material is by far the largest. So this means we can actually tune the water uptake of these materials quite nicely. We also see this leads to quite different zinc intercalation capacities, with the most hydrophobic material showing the highest capacity. And if we record impedance spectra at various temperatures, we can investigate the charge transfer resistance in these materials. Again, for the hydrophobic material here, we see at higher temperatures a decrease of the charge transfer resistance. So this is a typical activated process. We have a partial ion desolvation at the interface. and we can calculate the activation energy. But for the hydrophilic material, we don't see a temperature dependence at all. So this is an activationless process. So this tells us there's actually no desolvation or rather dehydration of the zinc at the interface. So again, nanoconfinement chemistry now can dictate the degree of hydration of intercalating zinc. Also with collaborations with Mosen and Axel from Ulm University, they have done ab initio molecular dynamics simulations, and they found that in the hydrophilic material we have here in green solvated or rather hydrated zinc in the center of the interlayer space, whereas in the hydrophobic material all zinc is pushed to the proximity of the V2O5 layers. And just if I have 1 more minute left, I want to show that this is not only a concept that works in vanadium pentoxide, but also in titanate materials. So here just a little image of a hydrogen titanate material where we also insert these ammonium pillars and expand it. We have shown for lithium that we can enable also solvent co-intercalation, but now I want to show you very recent results on the sodium intercalation in these systems. So we have just taken the standard sodium electrolyte and found that here in red and blue the expanded titanates showed a far greater sodium intercalation capacity. But if we look at the CVs, well, they are not looking super reversible. We have quite at a low rate already a shift in the oxidation and reduction peaks. So okay, there is an effect, but it's probably not a high power anode. But now, luckily, I had a master student in my group, Samra, who has now taken on the challenge to look at various different electrolytes. And what we have now employed is this Klein electrolyte that is famous for the sodium co-intercalation in graphite. And suddenly we saw already, wow, okay, we get extremely reversible cyclic voltammograms here, and they get more and more rectangular the higher the interlayer expansion is. And for the most expanded material here, we can look at CVs going up to 10 millivolt per second, and we maintain really beautifully reversible storage. So this is actually a high power sodium negative electrode now, we could say. Okay, so in summary, I hope to convince you that co-intercalation, so the switch from ion desolvation at the interface to the intercalation of partially or fully solvated ions, can actually be a really promising strategy. We can do this by materials design, and I believe this is extremely promising for post-lithium ion storage. And with this, I'm at the end of the talk. I want to thank all my group members, the collaborators, and the funding agencies, and you for your attention. Thank you.